Hello, my name is Yusuf, and I will now present our work in progress on automotive digital forensic. A bit about myself. I am originally from Jakarta, Indonesia, although I am currently finishing my PhD study in Cardiff University with a research focus in vehicle security. Apologies for not being able to present there in person. Unfortunately, my visa could not be processed in time. However, it has been a privilege to be presenting here recorded. We will start off with the problem. This simple sentence carries quite a challenge. There's two main ideas in it, which is the forensic readiness and evidence reliability. As all research problem, it started from literature review, but this particular problem of mine has also been discussed with the industry, such as Gareth from Thales UK, which is also a co-author. And I also have an end user, Rhys Dickinson, from the Welsh Police Collision Investigation Unit. I consider myself fortunate to have these real world connections and inputs during my study and research. To achieve digital forensic readiness, we must consider the entire incident lifecycle. The majority of research focus on the pre-incident, proposing encryption and gateways to prevent attack. Also, during the incident phase, where AI-based intrusion detection dominates. Our work focuses on the post-incident phase, although there are frameworks highlighting the need for automotive forensics. They often overlook the technical feasibility of gathering reliable evidence. This is the gap we are filling. We target four critical areas for technical implementation: capture mechanism, time synchronization, recording duration, and authenticity. Because while forensic happens after an incident, readiness is all about preparation, ensuring authentic, reliable data is available when it's needed most. It ties in perfectly with this question. Why should we care? Why should forensic readiness be an issue? Does it really need that attention from security researchers? Well, when an incident happens, you want an undisputed proof in chronological order leading to that particular incident to be recorded, especially if you are innocent. You want to have that capability, just like a dash cam. You don't wait until you're involved in an accident but doesn't have proof. You want it before, pre-incident. You want to be prepared. When we look at related work in in-vehicle logging, we see three main trends: mobile forensic apps, blockchain for integrity, and high-level frameworks. While valuable, these approaches often don't address the fundamental data collection issues. We also know from existing analysis that the standard event data recorder, or EDR, has its own problems. It provides an incomplete picture and is vulnerable to tampering. This is precisely why our work is necessary. We go deeper by focusing on four foundational pillars: the capture mechanism, time synchronization, continuous authentication, and recording duration. By addressing these, our work provides chronological context, increases confidence in the data's origin, and gives investigator a much wider window into the events surrounding an incident. To structure our research, we adopted the design science research methodology. We chose this because it's built around an iterative cycle of design and evaluation. This process is perfectly suited for a work in progress, as it allows for continuous refinement. The process begins with problem identification. In our case, the insufficient quantity and quality of data for forensic analysis. The following slides will walk you through the subsequent steps of our design and evaluation. Based on the identified research gap, we defined three core objectives to guide our work. First, enhancing automotive digital forensic readiness. Second, ensuring global time synchronization. And third, enable continuous ECU authentication. Together, these objectives aim to enhance forensic readiness and significantly increase the quality of evidence. To ensure focus and consistency in this phase of our research, we have scoped our environment specifically to the CAN bus, the most prevalent in-vehicle network today. Now let's translate these objectives into technical design choices. For our first objective, we enhance forensic readiness with two features. We move beyond the 20-second limit of a standard EDR with a recording duration limited only by storage. And we capture raw CAN frames directly from the bus in real time. For our second objective, we tackle time synchronization. To ensure timestamps are trustworthy, we use an independent, dedicated GPS receiver. We deliberately avoid using the vehicle's infotainment unit for time, as it's a known attack vector and its data could be easily manipulated. Finally, for our third objective, we address ECU authentication. We leverage the existing Trusted Unified Diagnostic Service, or UDS protocol. Our idea was simple. If ECUs already use UDS for secure one-off diagnostic, why not use it for continuous authentication? This highlights a key area for industry collaboration. This is what we come up with: a Raspberry Pi with a Pi hat for CAN communication, and also a GPS receiver connected to the USB port of the Raspberry Pi. To validate our design, we engineered this high-fidelity hybrid testbed. Testbed 1 uses an Arduino Uno with MCP2515 for emulating CAN bus. Testbed 2 starts with Euro Truck Simulator generating driving scenarios. The telemetry is extracted by SimHub and translated by an Arduino into a stream of physical CAN messages. These stream feeds both our logger and a real vehicle instrument cluster, which you can see here correctly reflecting the simulator's output. Well, you can't actually see it because it's quite small, but you get the idea. This setup offers advantages such as complete safety during testing and perfect reproducibility for scientific rigor. But most importantly, it delivers realism on three levels: scenario from the driving simulation, data from the authentic telemetry, and protocol. Our logger isn't seeing a simulation, it is physically connected to a real CAN bus, capturing a data stream that is indistinguishable from a production vehicle. Our initial results confirm the logger's core functionality. We successfully captured multiple long-duration logs from varied driving scenarios. Analysis of the traffic showed consistent, predictable CAN ID frequencies. Here you can see a snippet of the captured log. It contains the essential CAN data, but more importantly, our two timestamp fields. We have the internal system time from the operating system that the Raspberry Pi is running on, and the field for GNSS time and positioning. As expected, in an indoor lab environment, no satellite signal was available, but the fields are correctly implemented and ready for real-world testing. Next, we tested our most novel feature, continuous ECU authentication using UDS. Think of the standard UDS process as a bouncer, checking a technician's ID before letting them modify things. It's a trusted, secure handshake. We capture this baseline interaction where the ECU successfully authenticates and reports its correct firmware version. Then, We simulated two failure scenarios representing a compromised ECU. In the first one, the ECU fails to respond to the authentication request entirely. In the second, it responds but provides an invalid firmware version. Our logger successfully captured all of these interactions. For a forensic investigator, this log provides undeniable proof of an ECU state, whether it's a healthy one, unresponsive, or tampered with. Finally, we conducted a stress test to define the performance limits of our prototype. We flooded the bus with an increasing number of frames per second. The results were clear. At a typical bus load of 1,000 frames per second, the logger captured everything perfectly. At 2,000 frames per second, we saw minimal frame loss, averaging less than 1%. However, at a load of 3,000 frames per second, the performance degraded significantly, and we observed data anomalies. This test was successful. It only not proves the logger is capable of capturing frames up to a certain condition, but it also clearly defines the operational ceiling for this specific hardware prototype, informing future development. So let's return to the problem we started with, the lack of technical feasibility solutions for gathering reliable forensic evidence from vehicles. What do our results mean in this context? First, they mean our approach is effective. By combining independent time synchronization, continuous ECU authentication, and long-duration recording, we create a data set with rich, verifiable context. This directly enhances the reliability of digital evidence. Second, it means we have a viable solution. We've demonstrated a practical prototype that directly answers our initial research question. It moves forensic readiness from a high-level framework to a tangible piece of engineering, a step closer towards real-world implementation. For academic research to have real-world impact, especially in the automotive sector, it must be practical. That's why we assessed our prototype against key industry adoption metrics. First, cost. The hardware for our prototype costs around 120 pounds, maybe $150 US dollars, somewhere around that. This low cost makes widespread deployment economically feasible. Second, compatibility. It's designed for the standard CAN protocol, but is inherently future-proof for CAN-FD. It is entirely plug and play, requiring no modification to existing vehicle systems for repair or maintenance. Finally, system overhead. The impact on the bus is negligible. It operates in a listen-only mode, while adding only a handful of frames during its periodic authentication checks using the UDS protocol. We believe this kind of viability analysis is crucial, and we encourage other researchers to consider these kind of metrics to help bridge the gap between research and industry. In conclusion, we successfully designed, built, and validated a novel logging device that addresses a critical gap in automotive forensics. Our contribution enhances forensic credibility through independent timestamping and continuous ECU authentication. It also provides greater context by enabling long-duration recording that exceeds current standards. This work lays a strong foundation for several exciting avenues of future research. The immediate step would be testing this prototype in a range of real-world vehicles. Beyond that, we have identified three key areas for development. First, implementing robust encryption to secure the log data. Second, addressing privacy compliance through data anonymization techniques. And third, engineering a physical hardened enclosure to ensure the logger survives a crash. These are the attribution to the graphics I use in the slide deck. And thank you for the time and attention. This is my email. Because I cannot be there to discuss in person, do send your questions, inputs, or comments to this email, and I will make sure to respond to them all. Thank you.